Ranak everybody, today we will talk about why FEA engineers don't like linear tetra. You need to understand that in engineering there are not so many rules which are one for any question, for any situation and so on. And this is not from the list. So linear tetra is bad for mechanical problem, for linear problem, especially for problem with linear material behavior. But for some other type of tasks, for other type of solution, the rules can be different. So we talk about mechanical task, about task about stress, strain, factor of safety, and we talk about linear behavior of material. And it means that we talk about 80% of tasks. We don't talk about static or dynamic because it can be problem for static, for frequency, for stability, for buckling, for dynamic and transient tasks, and so on. But for some other type, it can be not problem, so please use this information carefully. Okay, why it's important type of elements and so on. This presentation was created for SolidWorks Simulation, and SolidWorks Simulation has only tetra elements and only three triangle elements for shell mesh. And the same problem you will have in a lot of CIE software which created for mechanical designer. So Autodesk, Inventor, Nostrum, and many others also will use the linear and non-linear or quadratic tetra elements and only tetra elements. Some of the big software like an MSC Patron, like Siemens FEMAP, like ANSYS can use very different very different type of elements. Also, it can use Prism, also which it can use pyramid, it can use hex element like this one, and so on. But in most cases, when we create mesh, the general mesh have a lot of triangle elements, a lot of tetra elements if we talk about 3D solid construction. And in some old book, in some old scientific papers, and in some old how to do the guides and so on, you can find information that for a lot of tasks you can use, but carefully, linear tetra elements. And for this task you need 2 or 4 elements for the thickness of your construction. And about these 2 or 4 elements through thickness we will talk later on the next video. Today we will talk about tetra elements. So why they recommend to use tetra elements? Because number of nodes create description of size of our problem. If we have construction which we mesh with 2 elements on site, we will have a couple of elements, we will have a couple of nodes, and the size matrix of stiffness of our task will look like this one. If we reduce element size 2 times, we obtain the mesh like this, and it increase number of elements 8 times for hex element. almost 5 times nodes we will increase, and the matrix will become like this one. If we use not hex element, if we use tetra, the situation can be something like that. And we need to understand that linear tetra has 4 nodes per element, and nonlinear or quadratic or tetra with mid-sides or second order tetra is the same. It's all the same. So the high quality in terms of SolidWorks simulation, high quality elements have 10 nodes. So it's 2 times more. So if you have the same mesh with the same density from linear tetra and from quadratic tetra, you will have difference in size 2 times. Difference in size of task, and you need different value and volume of resources. For nonlinear tetra, for quadratic tetra, you need 2 times more. So it means that you can reduce size of tetra and create finer mesh. And when computer was old, when software was old, and when engineers create mesh by their hand, and in any situation when they can, they change the solid mesh into the shell mesh or into the beam mesh, it can give a good result and a good understanding for people who know how to work with CIE software. But for now, most of the people, especially mechanical designer, only push the button and obtain the result. And if they use recommendation to use linear tetra, they will have big problem in reason of non-adequate description of stiffness of construction and non-adequate description of stress strain state. Even with very fine mesh, you can obtain some problem. In what reason? If you have a construction which are bending, you will have stress distribution like that. On the top, it will tensile. On the bottom, it's compress. When you have one element per thickness, it's try to create mean value depending on volume here. So it integrate stress distribution through this volume. In this reason, for this element, which almost doesn't have a volume here where we have the big tensile stress, we will have the zero tensile stress. Then we have not zero tensile stress, but not very big. And then we have bigger stress, which also means, but it's compressed. So we obtain something like this one. It's elements with not very high stress distribution, and it's constant. For linear tetra, it's always constant, because for linear tetra, we have linear distribution of displacement, and for strain and for stress, when we take the first derivative, we obtain constant stress here. So it will be constant and look like this. It's compressed, but closer to zero than for this maximum. And the next one elements which are present here, it's the same but opposite direction. So it has maximum volume here, so it will have tensile stress, constant tensile stress here. And in reason that stress in nodes we obtain from mean between all elements, we obtain something like 0 here. Not 0 because here will be additional elements with tensile, and here will be additional elements with compression. So here we have smaller tensile and smaller compression, even with these two elements. And that means that we obtain not only stepped distribution from elements to elements, compressed, tensile, compressed, tensile, compressed, tensile, but this constant value will be smaller than we need, and mean value in nodes will be also smaller. So we have very big problem with distribution. If we have two elements per thickness, it means that these elements will not mean compressive and tensile stress inside of one element if we have pure bending. So this element will have more intensive tensile stress because it have more volume here where it's higher stress, and less volume here where it's 0. And the next one will have less intensive stress, but the stress are higher than this because all stress which we mean here is all tensile. And the same situation for compression elements. And here we have not 0 stress in reasons that we have the same sign, the same tensile stress here. And here we have only compression, so it's also will be not 0. So this distribution much closer, but also will have some problem. But additional problem we will have if we have not pure bending. If we have bending and compression or tension, for example, we will have not this. If we have this one, tension, for example, we will have not this stress distribution, but like this. So the midplane with 0 stress will go like here. So it means that for this situation, for obtain not for only one situation with pure bending, but for more real situation, we need more elements on thickness for describing better stress distribution, for describing better stiffness. And now we return to stiffness. So what is the problem of stiffness? You can obtain good distribution of stress only if you have the adequate stiffness distribution from all of your construction in general. And the linear tetra affect this stiffness distribution. So if we take a look into how our strain distribute, and we have one element per thickness, we have 2 elements per thickness, 4 elements per thickness, and 10 element per thickness. We have here 5 elements through length, 10 elements through length, 12 elements through length, and 100 elements through length. And we can see type of stress distribution, and we need to understand that it's von Mises strain, so we doesn't have the sign, changing of sign, but we can see that here we have 1.6 E minus 3, and here we have 1.1 E minus 4. So it means that strain here is 10 times less than strain here, and not in reason of hotspots, not only in reason of hotspots, in reason of everything. So we see how it's try to mean stress and strain through elements, and we see that this almost zero and this more, in reason that here we have maximum volume here, and here we have maximum volume here. So if we create different type of mesh with 1 element per thickness, with 2 element per thickness, with 4 element per thickness, with 10 elements per thickness, and so on, if we create different number of elements per length, 1, 2, 5, 10, 20, and so on, we'll obtain different distribution of displacement. It's error of quadratic elements and from linear elements. Quadratic it's with mid-side. So, as you can see, we have the same error for linear task when we have 100 elements per length and 10 elements per thickness, and it's 0.65, and it's the same as 4 elements per thickness quadratic and 10 elements per length. It's almost the same. And the same mesh produce mesh with error in 30% for displacement. So description of stiffness have error about 30%. Here you can see different example with different mesh. This here you can see two type of picture. The top one it's linear, the bottom one is quadratic. Here 1 element per length, 4 elements per thickness, because someone told you that you need to have 2 or better 4 elements per thickness, so it's not only elements per thickness we need. Here we have 1 element per length and 4 elements per thickness, the same, but in reason of quadratic we have much more accurate stress distribution, even with 1 element per length. And you can check this picture. So this is linear, this is quadratic elements. You can check. This is strain distribution, linear elements, non-linear elements, linear elements, non-linear elements. And you can see a result, and you can see that non-linear elements were much more accurate, even on small number of elements. Also, we need to understand that tetra mesh it's very have very big fidelity for how does elements will go. Even if we have one point and this point is not hotspot, in reason of mesh which came like this one, or in reason mesh which like this one, in reason where the maximum volume we have for this element and what are the stress level on this place with maximum volume, we will have a very different value of stress. Here we have 30% of difference in one point in reason of different km stress, different variants of how mesh look like. So here we have one element per thickness and per length, one element per thickness, 2 elements per length, 1 element per thickness, 5 elements per length. This is linear element, this is quadratic element, this is linear element, 2 element per thickness, 1 element per length, 2 element per length, 5 element per length, and 10 elements per length, and quadratic element, and this is stress distribution. So you can see how it works and where you can find better distribution. And this example of bad distribution in reason of linear mesh. This is strain distribution, and you can see how it look like and how it work. And this is our displacement error for different type of task. All this line is quadratic element with 1 element per thickness, with 2 elements per thickness, with 4 elements per thickness. And all came something like this. Even 1 element, quadratic element, per thickness and per length will give result which are close to mesh 20 element per length and 4 elements per thickness for quadratic mesh. It's a huge difference. And this is why in most cases for frequency, for modal analysis, for linear static, for buckling, engineers don't like linear tetra elements because you need very, very fine mesh with very small element size, with very big number of elements, and with very huge number of resources and size of matrix to calculate adequate behavior. But you need to understand that for CFD task, it's not the same. For thermal task, it works in other way. If we talk not about tetra element, if we talk about hex element, it's not the same. Yep, quadratic hex element is much better than linear hex element, but it's not the same type of behavior. If we talk about electromagnetics task, it's not the same. They have their own rules and so on. So additionally, I need to say that even for mechanical task, we can have very different type of rules. For example, for explicit mesh, for explicit task, where used in most cases only linear elements, tetra elements can have some benefits with hex element, because hex element have something like hourglass effect, which can give some problem. So for high speed, high nonlinear task, tetra element can produce better result. For static and dynamic implicit task with big nonlinearities in material behavior, for example, for hyperelasticity or with big percent of plasticity in material behavior, lot of rules, lot of codes, lot of scientific work recommends, and even help of software recommend to use linear tetra and fine mesh. The reason that linear tetra is more stable for obtaining solution. Yep, you need much more fine mesh and you need a lot of resources to calculate them, but it's more stable. So use linear tetra in this type of task. If you have a question, please write in the comments below.